Welcome to Dr. Jimmy's Applied Calculus, Section 5.2, looking at extreme. So, something to do with values that are extreme. So, the idea is we take our charts into the boardroom. And we try to impress the board in different ways. And so we've already looked at that it depends on the situation. Sometimes we have positive slope, sometimes negative slope. And you say, oh, it's profit, so we're doing very well with an upward slope, not so good with a downward slope. But if it's cost, it's sort of the opposite interpretation. But the derivative tells us which way that is, even if we don't have a graph. Or using data estimates, we could look at that idea of the derivative, positive or negative. Now, we're going to be concerned with these points where things seem to change. So if we wanted to operate at the best profit, we would try to go toward a peak. So over in here, try to go this way. If we're in this part, we might have to consider this valley in trying to reach the best profit, because we may not be able to withstand this least profit to get to this even higher profit. So we may have to saddle ourselves to this profit or local. Locally, we're going to have to stick with this picture, sort of looking like this. So locally we get a peak. Okay. If on the end, so over here we also have a local peak, that same shape. One peak is higher than the other. And we also have this valley, which locally is the lowest. So, if we're trying to get the smallest, or the lowest, or the least, we would look for this trough or valley. But then we may be interested in this locally, because we may not be able to traverse over the peaks to find other possible low points. So let's look at these local points where you get the highest or the lowest. If we consider tangent lines and tangent directions or slopes, we've come to a point where the slope is 0. So we have 0 slope, but in terms of a function, that means the derivative is 0. So those very points that separated increase from decrease. So at a local peak, we have increase to decrease. We would have that picture. Local valley, decrease to increase. So these particular best or worst, depending on the interpretation, settings would be found where the derivative is 0, but we would have to have this change in direction. If there's no change in direction, then we would have pieces of a picture that might come to a 0 derivative, but then go back the other way again. So we have to test increase to decrease or decrease to increase, which again comes back to derivatives. So we need that change in sign of the derivative. So we investigated essentially this very thing in section 5.1 because we looked at the intervals where it increased or decreased. Now we just added this little bit, what's going on when it does change between the two. And so that would give us a peak or a valley. Now, more formally, a local highest point is a local or relative. That's another way we might state that. So we might say locally to our little neighborhood, this is the best. It's sort of like, who is the best basketball player? Well, if you look locally, so in your city, in your high school, in your college, it's much different than if you say, who is the best in the United States? And so, but another similar term would be relative. So relative to how far we look, here's the best or the highest. And the more formal mathematical term for such a creature is maximum. So we're looking for local or relative maximums. Okay. So we're not going to look everywhere. We're going to look locally, and graphically we see this peak type of picture. Okay. So all the functional values at, say, x sub 0 would be bigger than or equal to any other value. So that would make it the highest. So all other x, but relative or local to what we're looking at. And the local lowest height we would call a local or relative. We will use either term interchangeably. Minimum is the general math term for such a creature. So at a particular x, that minimum height would occur because it is less than or equal to in height everything else. So anytime we're looking for the least or possibly worst, those kinds of things are minimums. But worst and best are relative to what we're looking at. So the best profit would be a maximum. The worst profit would be a minimum. But if we ask what's the best cost, we would want a minimum. So those terms become relative, but together we're looking for one or the other, maximum or minimum. So together we call that an extrema, or the whole group, maximum, maxima or minima. So we might talk about them together, call them extrema, or we might look at them separately. The thing is, when we analyze this, either one, the mathematics involved is essentially the same. It's the interpretation at the end. Which one do we want? Let's return to this idea of maybe a boardroom. Sure. If we look at the entire picture drawn, and assuming that there aren't any restrictions which keep us local, then in this entire picture we see that there's a very highest point and a very lowest point. So one height is the maximum, but instead of local, it's global. The other word used interchangeably would be absolute. So absolutely, that's the highest. Or in the whole world, that's the highest. And then we have this other height down here, which is a minimum, but is, again, global for the entire picture being looked at. So a global or absolute minimum or maximum. So we have absolute extrema. Okay. So this depends on a much larger. So the possibilities would be a local, so it would already be tagged as a peak or a valley in the picture, and we would pick the highest peak or the lowest valley. But then because of restrictions in the picture or what we're looking at, there may be a point that didn't show up as a nice rounded peak or valley, but ended up at an end. So this may continue to another local peak. We don't know. It's cut off. There's the maximum height globally entire picture. So we'll look, sometimes we need local because we're not allowed or we have to analyze. Is it possible to find a higher point and be able to withstand a lower point? Or is it more practical we stay local? So, what we've seen is if we want to find extrema for y equal f of x, we would set up a set of critical values, I will say sometimes called numbers, but critical values for x. And so we saw in the setting that that could be solutions to where the derivative, which would represent the slope, where would it be 0? So that's a possibility. So each of those. Not necessarily will we get an extrema, but it narrows the search. So hence they're called critical values that we're going to look at. Now, sometimes we have a function defined, but there's no derivative. So we couldn't analyze that quite the way we did in those kinds of pictures. And so we would have to look at and add those to our list of possible critical values for the variable x. So let's take an example. What if our curve was given the second coordinate by 3x cubed plus 6x squared minus 18x plus 4. So we would hunt for critical values. In this case, where is the derivative equal to 0? And since this is a polynomial expression, it's continuous everywhere. It's nice, we have a nice derivative. So there won't be any places where it's undefined. So merely need, what are the solutions to 0 equal to 9x squared plus 12x minus 18? Let's see, we can factor out a common 3x squared plus 4x minus 6. Let's see, we have the derivative set equal to 0. I did a little common factor, but the rest of this probably not nicely factored. So we'll bring in the quadratic formula. And the 3 certainly can't be 0, so using the other part, it would be minus 4 plus or minus 4 squared minus 4ac all over 2a. We could reduce this and end up at minus 2 plus or minus square root of 22 over 3. Now, for some general purposes, not necessarily an exact answer, these two values are roughly approximated by minus 2.2 and 0.9. So this is enough to do what we're going to do next to get some test values. So I set up my number line, relative position of the two values, minus 2 minus square root of 22 will be close to minus 2.2, and the other one minus 2 plus the square root of 22 over 3, very close to 0.9. So we want to take some test x values so we're going to do what's called the first derivative test. And so I'm going to select test values in the 3 intervals here, cordoned off by those critical values for x. So I'll take an x which is less than this point, somewhat less than minus 2.2, so minus 10 would work okay. Between these two, I certainly know that one of these is positive and negative, so 0 should be in the somewhere in there. This is very close to 1, so I think I will select something different than 1, maybe 2. And so the first derivative test is to take the derivative and compute the value at each of those test points for x. So plugging this into the derivative, 3, and then I had factored out 3x squared minus, oh, we better check. I believe it's plus, plus 4x minus 6. So that would be 3 times 254, and certainly positive. Test the derivative, the first derivative, at 0. So 3 times 0 squared plus 4 times 0 minus 6. 3 times minus 6, certainly less than 0. And then make the last test of the derivative at the value 2. 3 times, this would be 14, so back to positive. So this is telling us it increases, decreases, and then increases. So more graphically maybe, we have it increasing, so a general upward slope direction. It goes across one of the critical values and becomes decreasing, and then at that point it goes back to increasing. So sort of visually we can see a maximum and a minimum. So these would be local or relative. So a relative minimum occurs at x equal minus 2 plus the square root of 22 over 3. And the minimum value is actually the height or the functional value at that x. So we would evaluate f at that. If I approximate that, minus 5.1531437. And a relative maximum occurs at the other critical value I found, x equal minus 2 minus square root of 22 divided by 3. And the actual maximum value would be the function evaluated at that, which turns out to be approximately 40.7086993. So we found a peak and a valley for local or relative situations. So what if we could be more global? So let's look at absolute maximum and minimum. So usually real problems present restrictions. Okay? We have to have at least so much resource to get started, and we can't have too much usually. We don't have infinite resources available. So we get situations with our universe or domain restricted in some way to some interval, such as what if we were restricted and we could only have the values minus 3 to 2. So we're going to look at critical points or critical values that would belong to that particular interval, and also the end points. Now we worked through information, but the original problem was just to find the absolute. We would take and line up these values. Endpoint minus 3, we have minus 2 minus square root of 22 over 3. A little larger than that, but certainly less than 2. We have the other critical value near 1, so not past 2 yet. So those are both in the interval, and the other endpoint. And it's a matter of comparing these four values. So we get minus 320 at minus 3. We have 40.7086993. We computed the local minimum, minus 5.153137 approximately. And then f at 2 is 16. So looking at this list, Here is the absolute minimum, and occurring at -3. Also in the list, we see the largest value is the absolute maximum. So one of these was originally a local maximum. The minimum occurred because we have an endpoint. Now, a very usual real-world restriction is that we don't have a negative amount of things. If we're going to invest money, we usually have at least something, not a negative amount. If we're going to build something, we at least need a positive amount of resources. So, 0 as an endpoint is not an unusual stipulation. And then there's usually some largest value of X. We only have so much money to invest. We can only obtain so many resources. So this type of interval. So this time we take the endpoints, and only one of the original critical values is in that interval, and that would be -2 plus square root of 22 over 3. So f of 0 was 4. We already have this approximation, -5.1531437. And we also had f of 3 turns out to be 85. So in that choice, we get the least of all of these, and we get the absolute minimum on that interval to be about -5. We find the absolute maximum to be 85. Now, for the very unusual cases that we have an infinite setting, so sometimes X might be time, so what's going to happen way off in the future. And so we might have a restriction 0 and then unbounded. So we could have just written this X bigger than or equal to 0. So now we want to check the endpoint, which we did at 4. And again, the only critical value bigger than 0 was the -2 plus square root of 22 over 3. Was that approximate -5. And then in some way we have this other endpoint. It's not really a point, but we have to consider what's happening. So we'll have to do X becoming infinite. What happens? And this is a polynomial with the leading term being positive, so that all ends up infinity. So we have still an absolute minimum in this situation, but there's no absolute maximum. So it will depend on the restricted domain in the problem, what's the absolute lowest point and highest. Sometimes it grows without bound, positive or negative, and you might not have a maximum or minimum. Now let's take another example. Y equals square root or absolute value of X plus 3. And look at this situation. we'll need the derivative. In the absolute value form, that might be more difficult. We could look at limits, but we could break this up into piecewise continuous parts. So if the value of x is non-negative, we can eliminate the absolute value. If x is negative, though, we'll have to change the sign. So if we put in a number like -2, we'll have to do minus a -2 to get back to +2. So we have the piecewise parts. And if we look at the derivative, if we stay away from the splice, we would see a derivative of x being 1. If x is bigger than 0, we would see -1 if we look at the other piece, which would be valid if we stayed away from 0, but x was less than 0. But we have at the place where the pieces are spliced, we have a functional value, but there's no derivative, so it's not defined at that point. So critical values, or I should have put in here, not defined, at x equals 0, the splice. So those critical values for x would be 0, and that's it. It's undefined, and certainly there are no solutions to derivative equal to 0 when it's 1 or -1. So we get a critical value, but it's not a 0 of the derivative in this case. So we'll do our first derivative test. So we have a 0. We need test values. So let's take -1 and 1. And so if we do the derivative, at -1, it actually is -1. It's -1 everywhere less than 0. If we take the derivative at +1, that's the part where it's always 1. So it's negative and then positive. So we get that it goes down, it crosses 0, it goes back up. So we do get a relative minimum. So it would occur when x is 0, but the actual minimum, that height, would be y evaluated at 0, which is 3.